Hello class, and finally in our coverage of chemical bonding we're going to discuss another theory called molecular orbital theory. And in the next slide we'll discuss how this theory was developed to help explain certain anomalies that were not well explained by VSEPR theory and valence bond theory. Note in this first slide that I show to the bottom right a hopscotch pattern, and you'll see the relevance as we explain molecular orbital theory. Sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi 2p star, sigma 2p star. Valence bond theory explains a great deal about the molecular geometries of molecules, but there are certain observations that are not explained by valence bond theory. It turns out that diatomic oxygen, the oxygen air we breathe, and certain other molecules are paramagnetic, and this is not explained by VB theory. Also, certain electronic transitions, absorption of photons going from one energy level to another, are not easily explained by valence bond theory. So another theory was developed called molecular orbital, or MO theory. Actually, when we say another theory was developed, I don't want you to think that valence bond theory and molecular orbital theory are competing theories. It turns out that VSEPR theory and valence bond theory together help explain the geometry of molecules, particularly those that have 3 or more atoms, whereas molecular orbital theory focuses primarily on diatomic species, for which VSEPR theory and valence bond theory really don't help us much because they're just linear molecules. Well, let's see what we're talking about here with MO theory. In MO theory, you start by counting the number of valence electrons provided by both of the atoms in the diatomic species, diatomic molecule, or diatomic ion. And then you draw a molecular orbital scheme, an example of which is shown in the bottom right of this slide. And you'll notice that I indicate what are called bonding molecular orbitals and anti-bonding, anti usually with an asterisk, anti-bonding molecular orbitals. A bonding orbital, as the name implies, is one where the pair of electrons that form that bond reside in an orbital that lies largely between, or circles, and lies between the 2 nuclei of the 2 atoms that are coming together. Whereas an anti-bonding orbital is one in which the electron clouds repel each other, and you actually form a node. Now, if you think about this, this is not so unusual because electrons do repel each other. So you may have wondered before, why do 2 electrons want to share the same sort of orbits, the same kind of space? Why wouldn't they repel? Well, they can share the same space if they have these opposite spins, but if they don't, they may repel. So molecular orbital theory essentially takes this into account, that there can be what are called bonding orbitals, where the electrons swim in between, largely in between the 2 nuclei, and anti-bonding types of orbitals in which the 2 electrons shun each other or stay away from each other, forming a node in between the 2 nuclei. And as you might imagine, anti-bonding, that doesn't sound like that would help hold the 2 atoms together. And it doesn't. So let's begin with an example and show how molecular orbital theory explains how a bond is formed between 2 hydrogen atoms. This is the simplest case we can imagine. And in such a scheme, on the left and on the right, we show the electron configuration of the 2 individual hydrogen atoms by themselves. And then we count the number of valence electrons provided by these 2 hydrogen atoms. And of course the number is 2, 1 from each, 2. And so we then distribute the electrons up to 2 for each orbital. A bonding orbital, what we call a sigma 1s bonding orbital, and possibly a sigma 1s star anti-bonding orbital. Well, you only have 2 electrons and they fill into the sigma 1s bonding orbital. Note that the subscript 1s means that this is a sigma bond formed from electrons that had existed in the 1s orbital of the 2 contributing atoms. Okay, that's essentially the explanation for the nomenclature. So in diatomic hydrogen, we would have 1 sigma bond, 1 bonding orbital, sigma 1s, and no electrons in the anti-bonding orbital. So you would predict that diatomic hydrogen forms a single bond. It has bond order 1, and that the 2 electrons are paired up. As I say in the bottom line, 1 good bond, no bad bonds. Well, let's go to helium. What if 2 heliums try to come together to form a molecule, to form a bond? Now, I know what you're thinking, but let's continue. The individual helium atoms have 2 electrons, they're 1s2, if we were to try to bring them together to form a bond, to form he, diatomic helium, we have 4 electrons to distribute. We put 2 in the sigma 1s bonding orbital, 2 in the sigma 1s star bonding orbital, and then we count the number of good bonds, that is, pairs of electrons in a bonding orbital, and we subtract the number of bad bonds, that is, pairs of electrons in anti-bonding orbitals. And in this case, we'd have 1 good bond and 1 bad bond. So we would predict that diatomic helium would have a net bond order of 0, and that essentially it wouldn't form a bond, and that's why we do not have diatomic helium. Well, how about 2 lithium atoms? Let's keep building up. Let's see how far this goes. The individual lithium atoms will be 1s2, 2s1. So they are to the left and the right, as you can see. And that gives us a total of 6 electrons to fill in. So just as with the 1s level, we could have a sigma 1s bonding orbital and a sigma 1s star anti-bonding orbital. Likewise, when we get to the 2s's, we could have a sigma 2s, you see, the 2s, because that sigma bond came from electrons that were in the 2s orbital of the individual atoms. We could have a sigma 2s bonding orbital and a sigma 2s star anti-bonding orbital. Okay, so we distribute the 6 electrons. We put 2 in sigma 1s, 2 in sigma 1s star, a good bond and a bad bond, and then 2 electrons in a sigma 2s good bonding orbital. So we would predict, in fact, that dilithium would have 1 good, 1 bad, 1 good, or a net bond order of 1. Now, this should not be surprising to the Star Trek fans, because Lieutenant Commander Montgomery Scott would have told you long ago that dilithium exists. It's not a very stable molecule. It's a high energy molecule, but he would have told you that dilithium exists. You might want to try diberyllium and see what you would predict. I bet you can predict it. Well, as we continue and consider nitrogen, 2 nitrogens come together to see if we can form dinitrogen, which of course we know we can. We continue to create a molecular orbital scheme. Now at some point, and you notice I've shaded at the bottom in blue, at some point we're going to focus only on the outer electrons, only on the valence electrons, because the 1s electrons, which form a sigma 1s bonding orbital and a sigma 1s star bonding orbital, those are always going to be filled in by the 1s electrons, and they essentially cancel out. You have a good bond, a sigma 1s bonding orbital, which is canceled out by a sigma 1s star anti-bonding orbital. So at some point we just ignore these and we call them core electrons, because they're not going to contribute to the bond order. They're going to cancel out. And so we're, from this point on, only going to look at the valence electrons. That is from 2s on, 2s, 2p. For nitrogen then, if we look at the electron configuration of the individual nitrogen atoms, it's 2s2, 2p3, right? 2s2, 2p3. That gives us a total of 10 valence electrons. And then we look at the types of molecular orbitals that we can form. We can form sigma 2s star, that is a bonding orbital and anti-bonding orbital, as we talked about before. Again, the anti-bonding orbitals are ones in which the electrons sort of shun each other and form a node in between the 2 nuclei. But also we have a new type of bonding orbital, a pi bond formed from electrons that had come from the 2p orbital of the contributing atoms. And there are 2 of these possible pi 2p bonding orbitals, then a sigma 2p bonding orbital, then a pi 2p anti-bonding orbitals, 2 of these, and then finally a sigma 2p anti-bonding orbital. So this is sort of our stack of possible molecular orbitals. And we fill in the 10 electrons. So 2 go into sigma 2s, a good bond. 2 go into sigma 2s star, a bad bond or an anti-bonding, or you can see that those are going to cancel out. And then we put 2 into pi 2p, then 2 more into pi 2p, and then the final 2 go into sigma 2p. Now, those last 3 are actually good bonds. They're bonding orbitals. So you would predict that the bond order of diatomic nitrogen is triple bond, which we already knew. See, this is consistent with the Lewis dot structures that we've been drawing for diatomic nitrogen. And you would also predict that all of the electrons are paired up. So diatomic nitrogen should be diamagnetic. So this is the general way the game is played. Now, if you look in the textbook, and I'll just show you the molecular orbital pattern that can exist, and this gets back to that hopscotch pattern, right? That can exist for diatomic species. And you can see that there's actually two molecular orbital patterns, the one on the left and the one on the right. And it gets to look a little complicated, yes, I know. And I'm going to ask you only to look at the molecular orbital pattern on the right, the hopscotch pattern on the right, which for the valence electrons at level 2 and above begin with sigma 2s, sigma 2s star, sigma 2p, pi 2p, pi 2p star, and then sigma 2p star. Okay, the stars mean anti-bonding, or the bad bonds. So if you look at diatomic oxygen, and this is an important reason why molecular orbital theory was created, to explain diatomic oxygen. If you were to fill in the valence electrons, you'd fill 2 into sigma 2s, 2 into sigma 2s star, so they're going to cancel, 2 into sigma 2p, 4 into pi 2p, and then the last two electrons into sigma 2p star. Okay, so let's first count the net bond order. Sigma 2s star, they canceled out. Then we have three good bonds, sigma 2p and the 2 pi 2p, so we got three good bonds. And then we have two electrons in the pi 2p star. Well, even though they're not together in the same orbital, we count any two electrons as a bond, in this case an anti-bond. And so we say here we have three good bonds and one anti-bond, or one bad bond. So that the prediction is that diatomic oxygen has a bond order of 2, which is consistent with our Lewis structures that we drew some time ago. But more significant, and the reason we have to invoke molecular orbital theory, is that it predicts that the two electrons in the pi 2p anti-bonding orbitals are unpaired, and that diatomic oxygen would be paramagnetic. Okay. If we continue on and look at diatomic fluorine, we have two more electrons to deal with. We have 14 total valence electrons. We place 2 in the sigma 2s, 2 in the sigma 2s star, 2 in the sigma 2p, 4 into pi 2p, 4 into pi 2p star. And if we count the number of bonds, you would see that it has a net bond order of 1, which is consistent with our Lewis structures for diatomic fluorine. And then the question is, does diatomic neon exist? You have 16 electrons to fill in. If you fill them all in, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, if you fill them all in, you would see that each bonding orbital is canceled by an anti-bonding orbital, so that you would predict that diatomic neon does not exist. Okay, so again, my advice is to pay attention to the molecular orbital scheme on the right in this slide. Now this slide just summarizes what we said. It says that molecular orbital theory helps explain why diatomic oxygen is paramagnetic and its bonding structure. But at the bottom paragraph it says, why don't you try some other diatomic species, and including some cations and anions, diatomic cations and anions, nitrogen oxide, NO+1, cyanide, O2-2, to try to determine whether or not these are diamagnetic or paramagnetic using molecular orbital theory. Again, use the pattern to the right, and what the net bond order would be. And in this last slide, I give you an example of the nitroxyl anion NO-1, which has a total of 12 valence electrons. Now, when you're counting the valence electrons, if it's +1 or -1, you have to count the charge. If it's -1 species, you have to add one more electron. If it's a +1 cation, you have to subtract 1 from the count of valence electrons. But NO-1 has 12 valence electrons, and I show on the left the nitrogen atom and the electron configuration of a nitrogen atom by itself, 1s2, 2s2, 2p3. And on the right, I show the electron configuration of an oxygen atom, 1s2, 2s2, 2p4, but I've also added one additional electron because the anion, NO-1, has an extra charge, so I just happened to place that electron on that side. And again, at the bottom, I have the core electrons, so let's not worry about them because they cancel each other out. And then let's place the 12 valence electrons into these orbitals. When you do that, you place 2 in the sigma 2s, 2 in the sigma 2s star, the anti-bonding, they cancel out, 4 into pi 2p, 2 into sigma 2p, and then the last two you would place into pi 2p star. So what would the net bond order be? Well, let's see. The sigma 2s and sigma 2s star, they canceled each other out. I got two pi 2p's, that's two good bonds. I got a sigma 2p, that's a good bond. So I've got three good bonds, and then I've got these two electrons in pi 2p star. We count that as one bad bond or one anti-bond, so the net bond order would be 2, and we would predict this species to be paramagnetic. Okay? So that's molecular orbital theory. So we finish this chapter on bonding. We'll then go into the next chapter in which we'll start talking about some real chemical reactions. We'll see you then.